on Functions Quick Start on Cloud Shell. I am Mahendra Mehra, your Senior OCI Instructor at Oracle University. This demo is divided into 4 steps. In the first step, we will set up our tenancy and ensure that we have suitable users and groups, appropriate compartments, VCNs and subnets, and finally create policies for the group and services. So let's switch to the OCI console and get started. I've already logged into my OCI console, and as part of tenancy setup, I already have a user account created which is part of a group. And let's go into the policies section and see the policies that I have set up for that particular user group. I'll click on the hamburger menu, go to identity and security, and here I'll click on policies. And here is the function policy that I have set up. The user that I'll be performing this demo with is part of the DevOps user group. And basically I've given the user group following permissions. So these are the policy statements which are required while you work with functions. And these policies can be referred from the OCI official documentation. You can also refer the previous video lectures where I've covered these policies in detail. The other important thing that is required to work with function is a VCN and subnet. I've already created them in my CTD OKE compartment. I'll click on networking, go to virtual cloud networks. I'll select my CTD OKE compartment. And as you can notice, we have a VCN which is already created with the name functions_demo. I'll go back to the home page. Now, as part of the second step of this demo, I will create our first application. I'll click on the hamburger menu, go to developer services and click on applications under functions service. Here we must ensure that we have selected the right compartment where we wish to create our function resources. In my case, it is CTD OKE. I'll click on create application. This opens up the create application wizard and I'll give it a name. I've provided a name for my application which is hello world-app, and the VCN in which I want to create this application is functions_demo. Under subnets, I will select public subnet. Just a quick information, a public subnet requires an internet gateway in the VCN, and if you choose private subnet, it would require a service gateway in the VCN. Now the next thing that we must select is the shape. The shape here represents the processor architecture of the compute instance on which to deploy and run the functions in the application. All the functions in the applications are deployed and run on compute instances with the same architecture. And remember, the functions image that we create must contain the necessary dependencies for the architecture that we select here. The shape options that are available are generic_ARM. If you always want your functions in the applications to run on compute instances with an ARM based architecture, then you must select this single architecture shape for your applications. And the functions image must contain necessary dependencies for the ARM architecture. And if you select generic_x86, the function image must contain necessary dependencies for the x86 architecture. You also have an option to select generic x86 ARM shape if you want your functions to run on compute instances with whichever architecture has sufficient capacity. In this case, OCI functions selects the architecture on which to run the function based on the available capacity. So if you select this multi-architecture shape for the application, every function's image must contain necessary dependencies for both ARM architecture and the x86 architecture. In our case, I'll select generic_x86 option and we'll move ahead. Also make a note that you cannot change the application's shape after you have created the application. Under tagging options, we can add tags to our resources. In this case, I'll skip it and click on create. There you go. Our application hello world-app is created. As you can see, it says active. Okay, once the application is active, we can use the getting started page to follow the rest of the instructions. Like I mentioned, in this demo, we are using the Cloud Shell setup. You can also go for local setup if you are comfortable setting up a local development machine. In this demo, we are sticking to Cloud Shell setup. So I'll launch the Cloud Shell quickly from the Launch Cloud Shell button here. For better viewing, I'll duplicate this tab and I'll maximize the Cloud Shell on this tab. Here I'll minimize it so that we can easily follow the instructions given in the Getting Started page. Alright, my Cloud Shell terminal is up. I'll clear the screen, press Ctrl L, go back to the first tab and start following the instructions given on the Getting Started page. The first command is fnlist context, which helps us find the name of the pre-created FN project context for the current region in which we've created the application. I'll copy this command and run it in the Cloud Shell terminal. As you can see, the region in which I am running this demo is the US East Ashburn region, and which is the region currently selected under the fnlist context output. The star here indicates that this is the current context. Just in case, if you wish to change the context, you can always use the fn use context and provide the name of your region where you want to run this FN project. For example, if I want to change the context from US Ashburn 1 to US San Jose 1, I will write fn use context US-San Jose-1. In my case, I'm happy with US Ashburn 1, so I'll skip that part. Next, we must update the context with the functions compartment ID. Our function will be hosted within the CTD-OKE compartment, and this page has populated the compartment ID as you can see over here. I'll copy this command and paste it in the Cloud Shell terminal. And as you can see, the output says current context updated with the compartment ID where I wish to run my function. Let's go back to the Getting Started page. The next step is to provide a unique repository name prefix to distinguish our function images from others. Right? When you run a function, a container image is created and it is hosted in the OCIR repository. So we must create a unique name and set it as a context for the registry. I'll go ahead and copy this command, paste it here, and simply replace the placeholder with hello world in Java. With this command, I'm updating the context for my OCIR, which is iad.ocir.io/my tenancy name / the name of my repository, which is hello world-java. I'll go ahead and hit enter. It says current context updated. Now if I hit the fnlist context command again, you will notice that under the US Ashburn context, the registry has changed to the registry that I just updated within my context. Now it's hello world-java. Previously it was functions_existing_image. Let's go back to the Getting Started page. Now the next step is to generate an auth token, which will be required while we do a Docker login into our OCIR repository. I've already created an auth token for this demonstration. If you wish to create an auth token, you can simply click on this link over here. It opens up the auth token page for you. And to create the token, you can simply click on generate token, give it a description and click on generate token. This generates the token for you. Copy it and use it for your authentication purpose. Although not given in the list of commands within your Getting Started page, one of the important commands that you must run is to update the context with Oracle image compartment ID. What this does is it configures the FN project context with the OCID of the compartment for repositories, to and from which our OCI functions will push and pull function images. Here I will paste my compartment OCID. So the compartment OCID is available here. I'll copy it and paste it here. Hit enter. And it says the current context has been updated for the Oracle image compartment ID. Now what's this? This will configure the FN project context with the OCID of the compartment for repositories to and from which you want your OCI functions to push and pull function images. In our previous command, we have updated the context with the registry information, and in this command, we have updated the context for the Oracle image compartment ID, which means whenever we run a function, the container image will get created within this compartment, which has been specified over here. what happens if you don't provide this information? If you don't provide this information, your OCI function will push and pull images to and from repositories in the root compartment. So if you want to restrict pushing and pulling images to root compartment, you must specify the Oracle image compartment ID where you want your functions to create your repository within the OCIR registry. And this is from where the OCI functions will pull and push images. Now to better understand this concept, I'll go to the OCIR service page. I'll click on the navigation menu, go to developer service, click on container registry. And this is the OCIR service page and the compartment selected is ctd-oke. If you notice, there is only one repository that is available at present, which is function existing image / hello java existing, and which has one image in it. But there is no other repository with the name hello world-java, which means when we run a function through the Cloud Shell, it will create a repository named hello world-java within our compartment ctd-oke, as we had specified the Oracle image compartment ID to be the ID of our ctd-oke compartment. And this will happen only after we create our first function. Now the next step is to log into the registry using the auth token. I'll copy the command. Go to the Cloud Shell terminal and paste the command here. The command is docker login -u flag, where we specify the username and specify the region key.ocr.io. The region in which I'm running this demo is Ashburn region, so the region key used is iad.ocr.io. I'll go ahead and hit enter. Now the prompt is asking for a password, which is the auth token. I'll copy my auth token and paste it here. I'll hit enter. And the prompt says login succeeded. We are now ready to start creating, deploying and invoking our functions. Now since this demo is getting a bit long, I'll pause here and we will continue in the next part. I hope you found this demo interesting. See you in the next one. Thank you for watching. Welcome back. Let's continue from where we left off in the previous demo. Now to create a hello world boilerplate function, we can use the fn-init command and specify the runtime parameter, specify the name of the technology that we are using for creating this boilerplate function and give it a name. I'll copy this command and run it in the Cloud Shell terminal. Hit enter. Well, the output says creating function at hello-java directory. It creates a directory hello-java where it creates all the function boilerplate code, including the function.yaml file. Now, if I move to hello-java directory and do an ls over here, we can see that we have the function.yaml file, a pom.xml file, which is basically a Maven configuration file that specifies the dependencies required to compile the function, and an src directory containing all the source files and directories for the hello world function. If we quickly look into the src directory, I'll cd into src, which has two different directories, main and test. I'll move into main directory, here Java, example and fn directory, and under fn directory we have a code which is hello function.java. Now let me quickly cat this file for you, that is display the content of hello function.java for you. I'll hit enter. Now what this function does is it takes as an input a string and prints hello and the string that you have provided as an input. In case you don't provide an input, it says hello world, right? So this is what this simple boilerplate Java function does. Let's also look at the function.yaml file. I'll open it using the cat command. Now if you look at the function.yaml file, the first line is schema version. This line specifies the version of schema used for the function.yaml file, and it ensures that the structure and the fields in the file are understood correctly by the functions platform. And the date format is year, month, and date, which indicates the schema version release date. Next is the name field, which specifies the name of your function. In our case, it's hello-java. Then comes the version, and this specifies the version of your function, and it's useful for version control and tracking updates or changes to the function. Here it is 0.0.1. Runtime set to Java indicates that the runtime for the function is Java, and the runtime specifies which language and framework are used. And in this case, it is of course Java. Then comes build_image, where we have set the path to the image, right? And this is the Docker image to be used to build the function. The image contains all the necessary tools and dependencies to compile and package the Java code. And as you can notice, it refers to a build image based on Java Development Kit JDK 17. Next is the run_image field, and this is again a Docker image that is used to run the function. This image provides the runtime environment needed to execute the Java code. And again, this image is based on Java Runtime Environment 17. The last line is the CMD line, and it specifies the entry point for the function. It includes the fully qualified name of the class and the method that should be invoked when the function is called. And here it is com.example.fn.hello function, which is basically the class, and handle request is the method that will handle the request. As you can notice, the class is hello function, and the method that it will be invoking is the handle request method. I will clear the screen here. Now we are within the hello-java directory. Now the next step is to deploy our function to the application that we have created in our application service on OCI. But before that, I would like to list the applications. So I'll run the fn list apps command. And as you can see from the output, we have just one app that has been listed that we had created as part of our previous step in the ctd-ok compartment. It's basically listing this app over here. Now I'll run the fn deploy command to deploy our boilerplate Java function to this application, which is hello world-app. The deploy function command is available in the getting started page. I'll copy this and I'll paste it over here. Now the syntax of the command is fn-v deploy --app, and you must specify the application name where you wish to deploy this function. In our case, it's hello world-app, which we just listed in the previous command. Once I hit enter, it will build the function and its dependencies as a container image, and that image will be named as hello-java. And that image will be pushed to the OCIR repository, and also the function will be deployed to the application that we just specified in our command, which is hello world-app. Let's go ahead and hit enter. Now let me decode the output for you. Now the moment I hit enter on this command, it created a temporary Docker file that will be used to create the container image for this Java function. As you can see, this is the content of the Docker file that is being used to create the container image for our function. Well, as you can notice from the output, the build has been completed successfully and the container image has been created with the name hello-java and the tag as 0.0.2. Now it's pushing that container image to the OCIR repository that we had specified while we updated the context. So the path at which it's pushing this image is iad.ocr.io/the tenancy namespace, and this is the repository where it's pushing the image, that is hello world-java. And from the output, we can confirm that the push has been completed successfully, and we can also notice that it has successfully created the function hello-java with the image that it just pushed to our OCIR repository. Now I'll go back to the OCIR repository, and now if I do a refresh here, you can notice the repository count has increased to 2 and the image count has also increased to 2. Now if I click on this drop down here, we can see that the repository has been created with the name hello world-java/hello-java, and it has one image in this repository. And the image is the one that was created using the fn deploy command and pushed into this repository here with the tag 0.0.2. Now if I go back to the first tab, our functions page, And if I click on functions, you can notice that the hello-java function has been created using the image as specified here, and the image digest is also provided. And here is the invoke endpoint that is available for you. Well, with this, we have created a function using Cloud Shell. Now, the next and the last part is to invoke the function that we just created. So to invoke the function, I'll go back to the Cloud Shell terminal. I'll clear the screen. I'll use the fn invoke command to invoke the function. And here you need to provide two parameters. The first parameter is the name of the application, and the second one is the name of the function, right? So the application name is hello world-app, and the function that is hosted within that application is hello-java. I'll go ahead and hit enter. And since we are not providing any string as an input to this function, it will just print hello world on the screen. Well, as you can notice, we've got an answer from our function saying hello world. Well, initially it takes some time for the function to run and return the results. And here in this case, it's hello world. Now, if I provide a string to this function using echo command, and this is the second invocation, this will be comparatively faster. Now, if I run the echo -n and specify Mahendra string as an input to the fn invoke command, I'll go ahead and hit enter. Well, as you can notice, this time the invocation was comparatively faster and it has returned hello Mahendra on the screen. With this, we come to the end of this demo where we've just created, deployed, and invoked our first function using Cloud Shell. I hope you found this demo interesting. I'll see you in the next one. Thank you for watching. Hello and welcome to this demo on creating a function from existing container images using OCI functions. Now, before I move on to the OCI console and start with the demo, I want you to know that when you create a function based on an existing container image, you specify function metadata to store in the OCI functions server. And this metadata include details such as maximum length of time the function is allowed to execute. And to begin with, the existing image on which you base a new function must be suitable for use with your OCI functions. Typically, to build and push a suitable image, you or someone else will use the fn project CLI commands or the docker CLI commands, right? For instance, after writing your function code and creating a function.yaml file, which contains your function metadata, you can use the fn build command to build a new container image from that function, and it also pushes the container image to your specified OCIR repository. We saw this in our getting started with functions using Cloud Shell demonstration. Now, once you have that image in your OCIR repository, you can use the functions console to create a function based on that image. Right, so as part of this demo, I have already created an image that we'll be using for this demonstration. I will now switch to the OCI console and continue with the demonstration. Well, I've already logged into my OCI console and this is my OCI dashboard. And for this demonstration, I've already created a container image which is hosted in our OCIR repository. I will show it to you, and for that, I'll click on the navigation menu, go to Developer Services, click on Container Registry. And within my CTD-OKE compartment, I already have this repository with the name function existing image / hello java existing. And if I click on this repository, and if I click back on this drop down here, you can notice that there is an image that's already available with the tag 0.0.7. Now we will be using this existing image to create a function. In our earlier demonstrations, we saw how to create a function from scratch, where we use the boilerplate function. And in this case, we'll be using the container image that already exists in your repository. Now, to create the function, I'll move to the function service page. So I'll click on the navigation menu, go to Developer Services and click on the applications under functions category. Now we can create this function in an existing application that's available, or we can create another application and host our function in that application. In our case, I'll create it within the existing application. So hello world-app is the one that I'll be creating the function within. And as you remember from our previous demo, we already have one function that is part of this application, which is the hello Java function. Now I'll click on this create function drop down, and as you can notice, we have this option to create from existing image, right? I'll click on the create from existing image option. This opens up the create function wizard, and here I'll give it a name. Let's name it hello world Java existing. The next field is to select the repository from where we wish to select the existing image. And if I click on this drop down here, we have two repositories, right? And we will be selecting the first one. This is where we have hosted our existing image, right? So I'll click this. And within the image field, we need to select the image. Since this repository has only one image, there's only one entry for the image with the tag 0.0.7. I'll go ahead and select this. Now, one important thing to note here is that the image you select to create a function from an existing image must be compatible. Its architecture must be compatible with the application's shape where we are hosting the function. Now, since we are hosting this function, which is named hello world Java existing within the hello world app application, and the shape that we had used for the hello world app application is generic x86, there must be compatibility between the container image that we're using to create the function and the application's shape that we had selected earlier. Now the next field is where you define the maximum amount of memory the function can use while running, and the options are from 128 MB up till 2048 MB, which is 2 GB. I'll go ahead and select 256 MB. Under the timeout field, you can set the maximum amount of time the function can run, and here in this case it is set to 30. I'll leave it to the default. The next field is provisioned concurrency. This helps you minimize any initial delays when invoking the function. Now if we enable this provisioned concurrency, we have to specify the provisioned concurrency units. When you enable the provisioned concurrency field, you must specify the provisioned concurrency units. Since I've selected the memory as 256 MB, the provisioned concurrency units must be specified in multiple of 20. I'll use 20 as the value for this demonstration, and I'll move ahead. Under tagging, you can specify the tags for your resources. I'll skip this for now and click on create. As you can notice, the hello world Java existing function is now active. Now we'll go ahead and invoke this function. Now to invoke this function, I'll use the fn invoke command, and for which I'll switch to the next tab where I already have the Cloud Shell terminal up and running. I will use the fn invoke command to invoke this newly created function. So the command is fn invoke. We specify the application name where we have hosted the function, which is hello world app, followed by the function name that we are trying to invoke. And the function name, like I mentioned, is hello world Java existing. I'll copy this and paste it here. I'll go ahead and hit enter. And it says, hello world, welcome to this demo on creating function from existing container image. Right, so this is what the function returned when we invoked the function. Now, similar to the earlier demonstration, if we provide a string as an input to this invoke command, it will replace the world string with the string that we pass as an input. So I'll use the echo command here and pipe it to the fn invoke command. Let's hit enter. Well, the output says, hello Mahendra, and welcome to this demo on creating function from existing container image. Also, you can list the function that we just created under the applications page. I'll click on the application again. And if you notice, we have the two functions that are hosted under this application, hello world app. One is the hello Java function that we created using the boilerplate function, and the other one is the hello world Java existing function that we created using an existing container image. Now, if you wish to delete an existing function, you can click on this action menu and click on delete. This will delete the function for you. You can also edit the function details by clicking on edit, and this opens up the edit function wizard where you can edit the function to specify more memory for the function, And you can also edit the timeout for your function. You can also change the PCU's value for the function. And once you do that, you can click on Save Changes. And the new changes will apply to the function that we just edited. So if I click on this function now, you will notice that the memory has updated from 256 MB to 512 MB. To delete the application and all the functions within it, we must go to the applications page. And here you can simply click on this action menu and click on delete. This will ask you to enter delete hello world app before continuing. And once you enter this string over here, it will delete the application and all the functions that it's hosting. Well, this concludes our demo on creating a function from existing container image using OCI functions. I hope you found this demo interesting. I'll see you in the next one. Thank you for watching. Hello and welcome to this lesson on managing functions in OCI. In this session, we'll delve into several key aspects that are crucial for ensuring the smooth operation and performance of OCI functions. So let's get started. Resiliency and availability are paramount in ensuring the uninterrupted operation of systems even in the face of failures or degraded performance. In the context of OCI functions, resiliency refers to systems' capability to withstand disruptions, while availability signifies its ability to remain accessible to users. The architecture of OCI functions comprises two essential components, the control plane and the data plane. The control plane handles functions definitions, while the data plane executes functions upon invocation. This separation of responsibilities allows for efficient management and execution of functions. OCI functions prioritizes resiliency and high availability by distributing its control and data plane components across multiple availability domains and fault domains within a region. This distributed architecture ensures that if one domain experiences an outage, the system can seamlessly switch to alternative domains to maintain uninterrupted function management and execution. When invoking functions, it's essential to adhere to best practices to optimize resiliency and availability. Designating a regional subnet for an application or leveraging multiple availability domain-specific subnets enhances fault tolerance and ensures continuous function execution even during domain failures. Let's understand two fundamental concepts, concurrency and scalability. Concurrency refers to a system's capability to run multiple operations simultaneously using shared resources. Scalability, on the other hand, is the ability of a system to adjust its capacity, both increasing and decreasing, to match the demand. When a function is invoked for the first time, OCI functions deploy the function's image as a container within a specified subnet. The function running inside the container can interact with other shared resources and services such as databases and object storage, ensuring seamless integration and operation within the cloud ecosystem. OCI functions excels in handling multiple simultaneous requests through automatic horizontal scaling. When multiple calls are made to a running function, OCI functions efficiently starts additional containers to handle the load, up to a limit specified for your tenancy. By default, this limit is 60 GB of RAM reserved for function execution per availability domain. This automatic scaling ensures that response times remains consistent regardless of the number of incoming requests. Another crucial aspect is the isolation of function executions. When functions from different applications are invoked concurrently, OCI functions ensures that each function runs in isolation from others. This isolation prevents any interference between function executions, maintaining a secure and efficient environment for all running functions. Next, let's discuss reducing initial latency using provisioned concurrency. When a function is invoked for the first time, often referred to as cold start, OCI functions provisions the function invocation with the necessary execution infrastructure. This includes the compute and network resources required for the function to execute successfully. The initial provisioning and response to this first invocation might take a variable amount of time, potentially several seconds or longer. However, once the infrastructure is in place, subsequent function invocations, also known as hot starts, can make use of existing infrastructure. This typically results in a sub-second response time to the function invocation. To ensure that the execution infrastructure required for a function is always available and to minimize any latency associated with initial provisioning, OCI function supports provisioned concurrency. Provisioned concurrency allows OCI functions to always have the necessary execution infrastructure ready for a certain minimum number of concurrent function invocations. This is measured in provisioned concurrency units or PCUs. The total number of PCUs available for your functions depends on several factors, like the size of the function, the tenancy limit, and whether provisioned concurrency has been enabled for other functions in the tenancy. To use provisioned concurrency effectively, you need to specify the number of provisioned concurrency units or PCUs required for your function. It's generally a good practice to match the number of PCUs to the number of concurrent function invocations you anticipate. The amount of memory you allocate to a function directly influences both the minimum number of PCUs you can specify and the increments by which you can increase these PCUs. This ensures that your function has the necessary resources for optimal performance and minimal latency. By carefully specifying PCUs and understanding the relationship with the available memory, you can ensure that your functions are always ready to handle incoming requests with consistent sub-second response times. As you can see, the PCU's value must always be a multiple of 10. If the available memory is 256 MB, the PCU's value must be a multiple of 20. And if the available memory is 128 MB, the PCU's value must be a multiple of 40. You can specify PCUs for a function in two different ways. Using the console when creating a new function based on an existing image that has already been pushed to the Oracle Cloud Infrastructure Registry, or while using the Oracle Cloud Infrastructure CLI to create or update a function and specifying the optional provisioned concurrency option. Let's take a closer look at the provisioned concurrency option. The format is as shown on the screen: provisioned concurrency with the following value. Here, strategy indicates whether to use provisioned concurrency. So if you provide the value as constant, it means you're using the provisioned concurrency. And if you don't want to use the provisioned concurrency, in which case you must specify none. Count here indicates the minimum number of concurrent function invocations, and this applies only when the strategy is set to constant. For example, in the OCI fn function create command as shown on the screen, note that the provisioned concurrency parameter must be in the valid JSON format, which depends on the platform you are using. You can provide the parameters as a string at the command line, as a file, or as a command line string and as a file. You can also update an existing function to specify the provisioned concurrency or update the provisioned concurrency, where you just need to use the OCI fn function update command and specify the function ID with the provisioned concurrency parameter and supply the values that you wish to update your function with. To wrap up, in this lesson we covered essential concepts and best practices that ensures your OCI functions are resilient, highly available, and capable of scaling to meet demand. I hope you found this lesson informative and helpful. I'll see you in the next lesson. Thank you for watching. Hello and welcome to this lesson on functions integration with OCI services. My name is Mahindra Mehra and I am a senior OCI instructor with Oracle University. In this lesson, we'll explore the integration of Oracle functions with other Oracle Cloud Infrastructure services. Additionally, we'll explore how to access other OCI resources from running functions. So let's get started. First, let's discuss how functions can be triggered. OCI offers several services that can automatically trigger functions for you. These includes the event service, which can invoke functions in response to specific events, and the API gateway, which can expose your functions as API endpoints. Additionally, you can manually trigger functions using the CLI and the SDK, giving you flexibility in how and when your functions are executed. Once a function is triggered, OCI functions pulls the corresponding Docker image from the OCI registry and starts the function container. This allows for efficient and scalable execution of your code. While your function is running, it has access to a wide range of downstream services. For example, your function can interact with object storage to read or write data, connect to an autonomous database for advanced data processing, or leverage compute resources for additional computational power. It can also securely access sensitive information using the secrets service, manage networking configurations, and much more. All the logs, metrics, and traces generated during the function execution are automatically sent to OCI's logging, monitoring, and application performance monitoring services. This integration ensures that you have comprehensive visibility and insight into your function's performance and behavior, helping you maintain and optimize your applications effectively. With these integrations, OCI functions provide a powerful platform for building, deploying, and managing serverless applications that can interact with a wide array of cloud services, ensuring your solutions are both flexible and scalable. Let's take a look at the steps required to enable a running function to access other Oracle Cloud Infrastructure resources. To begin with, we must create a dynamic group for the functions. It totally depends upon your use case. If you want all functions in a compartment to be able to access a resource, enter a rule similar to the following on the screen. This rule adds all functions in the compartment with the specified compartment OCID to the dynamic group. As you can see here in this example, the dynamic group name is Acme function dynamic group, and we are adding all the functions in the resource.compartment ID whose compartment OCID we have specified in the dynamic group rule. If you want a specific function to be able to access a resource, then you must enter the rule as displayed on the screen. Here you add the function with the specified OCID to your dynamic group. And the rule is resource.ocid and specify the OCID of your function. And if you want all functions within a specific defined tag to be able to access a resource, then you must enter the rule as displayed on the screen. For example, if you want to specify all the functions with a specific tag in your dynamic group, you use the rule all resource.type, which is set to fn function, and specify the tag name and value. Having created a dynamic group that includes the function, you can now create a policy to give the dynamic group access to your required OCI resource. If you want your function in the Acme function dynamic group to be able to get a list of all the VCNs in the tenancy, you must specify the following rule, which allows your dynamic group Acme function dynamic group to inspect VCNs in tenancy. If you want a function in the Acme function dynamic group to be able to read and write to a particular object storage bucket, then you must enter a rule similar to the one given on the screen, which allows your dynamic group to manage objects in a given compartment. You can also have a specific rule where you can use the where clause to specify the bucket name. If you want your functions in the Acme function dynamic group to be able to read and write to all resources in a compartment, then you must enter a rule similar to the one given on the screen, which allows your dynamic group Acme function dynamic group to manage all resources in the compartment, and you must specify your compartment name or replace it with tenancy as per your use case. The third and the final step is to include a resource principal provider in the function code to enable the function to authenticate with other OCI services. First, let's discuss how authentication works with the resource principal provider. This provider uses a resource provider session token, also abbreviated as RPST, to authenticate functions with other OCI services. This token ensures that functions can securely access the necessary resources defined by their policies and dynamic groups. Next, consider access control. The RPST is only valid for resources that the dynamic group has been granted access to, making it a robust mechanism for enforcing access policies. This helps maintain strict control over what resources your functions can interact with. An important aspect to note is token caching. The RPST is cached for 15 minutes, which means any changes to policies or dynamic groups will take up to 15 minutes to be effective. This caching mechanism helps optimize performance while maintaining security. When it comes to implementation, we recommend using the resource principal provider included in the OCI SDK. This SDK streamlines the process, ensuring your functions can easily authenticate with OCI services. Alternatively, if you prefer not to use the SDK or are working in a language it doesn't support, you can write custom resource principal providers using environment variables and files within the function's execution environment. Let's go through the Python code example, which shows how to use the Oracle Resource Principal Provider to get a list of virtual cloud network from the Oracle Cloud Infrastructure. The statement import IO is basically importing a core Python library used here for handling IO operations. Import JSON, a core Python library again used for working with JSON data. From FDK import response, this line is part of the FN project's FDK for creating responses in serverless functions. And import OCI is to import the Oracle Cloud Infrastructure SDK used to interact with OCI services. Handler here is the main entry point for the function, called when the function is invoked. Here, CTX is the context object, provides information about the function invocation. The data object contains the input payload of the function invocation. Signer equals to this line gets a resource principal signer, which is used to authenticate the function with other OCI services using a resource provider session token, also known as RPST. The next line here calls the do function, which is defined later, with the signer as an argument and stores the response in the response variable. The next line, which is return response, this line returns the response from the function. It converts the response data to a JSON string and sets the content type header to application/JSON. Do signer is the function that performs the actual logic of listing the virtual cloud networks. Here the client line creates a new instance of the virtual network client class from the OCI SDK using the resource principal signer for authentication. The try block contains the code that may potentially raise an exception. This line calls the list_VCN method on the virtual network client instance to get a list of VCNs in the compartment associated with the signer. The signer.compartment ID provides the compartment OSID. The next line over here processes the list of VCNs returned by the list_VCN method. It creates a list of lists where each inner list contains the VCN ID and display name. If an exception occurs while listing the VCNs during the list_VCN call, it is caught here. If the exception is caught, the exception message is converted to a string and assigned to the VCNs variable. And this last line returns the list of VCN or the exception message in a dictionary with the key VCNs. In a nutshell, the handler function is the entry point to the function invocation, which gets a resource principal signer and calls the do function. The do function uses the OCI SDK's virtual network client to list the VCNs in the specified compartment and returns the list in a structured format. The response is returned as a JSON object with the list of VCNs or an error message. To wrap up, we have covered the integration of Oracle functions with various OCI services. We have also explored how to access other OCI resources